Arrows are pointing in different directions.
And then you use the hint is right here, but it says like these B's become rows. So that's even enough.
Thank you.
So then that means one. It's I don't yet see where that.
Oh, and then you're just doing square.
This square.
So also what happens if you have like a derivative acting this way, derivative acting this way, you multiply them together like that.
Observe.
Yeah.
Yeah, but
What's that?
because it's
The way I interpret this, which might
it's half.
be right.
Half existence.
Yeah.
This one is a potential.
Yeah, exactly. And then the local potential, I think.
This guy. It's two. This guy. Yeah, I would like it. So that takes the expectation value.
It's very.
You guys done with the problem one? I just noticed that the problem one is very challenging. Okay, so because you need to figure out there's an identity you need to use. So I wrote my answer there, so.
Yeah.
Can you put the identity like somewhere written on the board so folks know which one? Or what? No. I was thinking just right. Oh,
Keep it broken, you can't do this identity.
Last year.
No.
This is the. No, I don't know if get this. No. Yeah. Improves.
I really need to prove how it's judgment. Just pretend I can do that. It should have worked without. But now I get this. I don't know why I'm trying to normalize. Well, I forgot to apply it twice. This is just the first term. And then you try to solve what with this operator. Oh no, I have harmonic oscillator. Yeah, so I construct the matrices of A and B. So B, I take it. I take triangular tri-diagonal matrix, but I'm playing around. I probably did something wrong too. But it's clearly wrong. I don't notice it. Divided by 2x. Divided by 2x. X, yeah, but dx. Dx, 2 dx. won't change much. Try without this boundary stuff.
They do that efficiently.
Yeah, there's NP.
That's a shift.
It's an extra function. Races.
They don't start to do this.
Oh, that's because that expression. Gradient of the full thing, right? And there's the gradient up top. So you have two derivatives, right? Like one more.
Did it.
So it's not the dx squared. Like there's one derivative for this one, for the epsilon times it, that's the dx. And then you have one more for the opposite, right?
One because of the DA.
Yeah, but you need to make sure.
Oh, yeah.
We have your focus on your life focus.
Yeah.
So as a Yeah, I think so. So I think that's what I said, like it's it's a mix, it's not just a proposal, right?
It's normal as a trace. But this is this right? I remember one was like the shape of the eigenvalue.
Yeah, but I can say. What's your
I think you said you could try notebook 10 sometime because I want
I mean, they mostly want to see what you're generally interested in. Of course, if you have like a very specific project that you'd like to work on, then
cool.
I think I definitely played with like margins and yeah, like my font sizes.
Okay. Around there.
Okay.
That's fine. Right?
Yeah, no, that's usually fine. And then just don't share it with anyone else.
Yeah, but why then is that normalized?
It's normalized. Did you have a clear mindset of what did you want to work with?
Yeah, when I applied it was like, as you will see, it's mostly honest. Obviously, for any job, I recommended that you also say other names.
No, I mean, this would sum to.
What will you want? Because
Yeah, that's mostly like two, with the two, like the main names that you have to work for. The other ones are mostly for, I could envision myself collaborating. Now that I know a little bit more, proposing anything with it, it's not like we don't share the same research interests at all. So, but
Should.
I think they have some guidelines on what to write. Because I think it has it's a little bit what you're currently interested on, what you'd like to do here, which you would like.
Yeah, but I just don't get the question.
Career goals, because in the end it's only 3 years, right?
were you already
doing light matter stuff, or did you already know light matter stuff before? I was doing regular science things, so but I remember even when I started my PhD, reading papers, I was just like, oh, this is cool. I had some ideas, but I didn't have a paper on because I had to go this. But I knew back then that something really. I might have. Was there not? If I've done it, maybe by the time I'm done, I will be more. Which I think it's fine. You can just put it as like in progress. As long as you discuss what you've done and those things, how they, yeah.
Wondered would be
It's a computational center, right? So they want to know, like, what kind of programming experience have you had? Like, adding something like that is a good addition. Yeah, it's electron affinity. Okay, so of course, they also use that. So, of course, Information theory for correlated methods or use better workers. So we develop this extension of optimize workers for actually it does effectively it's two responses. It's just like the EFT, but it is also two
Same thing.
which one is when you like wrote it 1.5?
the correct result. No equations, okay. It's gonna be. So,
I'm not sure if I can.
first exercise. Oh,
Yeah.
just make it like fresh.
My body is supposed to be salty.
It's nice.
And those instructions.
Yeah, after 5, I'm going to upload it.
I can just differentiate these.
Or just me.
So I need some, yeah, depending on.
Because I want to print all. You have X and then a bunch of other things. Other colors. That's fine.
It's just the value. I just.
This will not differentiate that.
This one, not yet. So we have this.
Fine. Fine. Just forget it. Oh, I know.
How many people are still stuck in problem 1? Okay, so I mean, like, I think this is some mathematical challenge here. Maybe I can just go through very quickly. So I mean, like, we start from the, let me see.
And then do that.
Plus this term. This.
So we start from this, I mean,
Wait.
so we start from this, I mean, like equation. And so basically now we are in 1D. So basically I transfer every gradient
And then you still have.
or like Laplace
Integral.
to like a derivative along one direction. Okay, so everything about this becomes a derivative along a x direction. So the next thing is that I kind of like do compute distance for one particle. So I use this definition. Okay, and inside this definition, basically I need to compute the expectation value. So there's a psi star and also psi phi here. And in between, basically, this is the first term is from this J operator. And the second one basically is also from the definition for this current paramagnetic current operator. And the next slide I do is like I do the integration by part. Okay, so I transfer this one to the first side, the first one. And after that, basically I can take advantage of this Dirac delta function. So I get rid of everything like from the integration. So at the end, I got this formula for this small f. And because now for the one particle, this wave function, we can choose a real value. And for one particle wave function, basically we can compute this wave function from the electron density. Okay, so we just take the electron density, the square root of this one. And because if you go back to this formula, you are going to see there's a CC, it means a complex conjugate. So because everything here is a real, so we get rid of this 1/2. Okay, so at the end of the day, basically I write down everything here. And you are noticing here there's a gradient, like a derivative along x, and this is also a derivative along x. And the first thing is that I got rid of this one, and there's a 2, so they disappear. And the next thing is that I compute this term. For this term, I take the derivative. Basically, at the end, you are going to get this one. Okay, and this one you have to use a vector calculus identity. So show below. And then basically I transfer, I multiply this phi square to the other side. And this phi basically is this one. Sorry, there's a typo here. Okay. So once you do this transformation, then basically the numerator becomes a phi square times this guy. So phi square, this guy will cancel with this one. Okay, so at the end, basically you are getting this result, and you get rid of this one. Then this is a final result. Sorry. I didn't know it's too challenging. Yeah. Okay, so let's go back to the.
The derivatives on B, are there some constants you neglect or?
Yeah, you can also have like constant, but it doesn't affect like if you have a potential and if you have a constant shift of a potential.
For example, the first derivative, so you could have a constant in the gradient of potential, that would affect things, right? So with the first one, you get rid of it.
Another way is like instead of like get rid of the let's say if I don't get rid of this, I still keep that. And if you use this one, then at the end you are going to see this is a square and square. So you mean like there's a kind of like a linear term there?
Yeah.
Oh, what is a linear term? Is that physical?
It doesn't make sense to have a linear term, right?
Yeah, but I mean like I don't have any intuition about why the linear term disappear. But if you have a linear term, basically it means it's unbounded. Yeah.
Well, unless you have a quadratic.
I mean like if you have a linear term, potential linear term, basically you can always go to the infinity.
What if you have a quadratic? Quadratic plus linear is still bounded, right?
Yeah, but like if you do the quadratic term, and basically this form there's a constant, but at the beginning there's no constant. Yeah. I mean, like here there's no constant, so does that make sense? Oh yeah. Okay, now it's time for break. Okay, it's time for break. You need to solve the partial equation, and basically you need like a boundary condition, and usually like the potential it will vanish at infinity. So that's why if you have a linear or quadratic term, then we have to make it like disappear. It depends. Yeah, at infinity.
Problem with this example was that it was finite box.
It was
Finite box.
finite box.
Yeah. I want an infinite box, you know. I want a finite number.
Another pen. Another pen.
And you passed it.
It's terrible.
Worth it.
Once again to rate.
I still can't hear you.
With what? No funds? You will waste, you spend all the money on the funds.
No.
So I cannibalize the ink cartridge from another pen. And,
You cannibalize it.
because,
So that's why I said it's single payment.
A single payment in 100 years. So
Oh,
100
in 100.
Yeah. I can be you halfway there.
Jumped it.
50 years. Halfway there.
so then I said,
I'm not sure if I can make
look
it.
it over again. I just smashed it. Quickly. So when you do that, I was afraid that ink was going to go everywhere. It worked. It worked.
Sometimes violence is.
Twilight was more like
Question, man. So how should I be thinking about this expression for the exchange correlation curve? Is that like, it's related to the curvature of the density?
Yeah, that's right. You can think about it's like you
Right.
can do the this
Yeah.
yes, like for example, you are corresponding to
It's like, it's less of a cool story. It's like not a cool
story. French steam. Well, that's travaux pratiques. Travaux pratiques. Like practical work.
Basically, you are doing something like a curvature along the polarization direction.
So the direction that density increases.
Yeah, because here you need the first thing is that you have a gradient.
Oh, it's a.
Yeah. Now we are looking into like the projection, the polarization direction.
应该也有一个就是大块儿。
You have to have some.
其实我就觉得这个
It's
LDA
a Laplacian, so it's kind of like a Poisson solver. So for the Poisson equation, basically, if you have some like a source term on the right hand side, it's going to generate some like a kind of like a source charge there, and then you will generate a potential. And this potential, this source term basically depends on the curvature with the electron density. So if you have your electron density change very quickly around some region, and it means you will generate a large light matter coupling there because you have a more electron very close to each other. So once there's a one electron, basically you will feel like you will propagate the light matter interaction.
Oh, that's interesting. What happened to the photon wave function? Did that vanish from the problem at some point?
So the wave function basically now what we are doing is like we look into the matter potential itself. And in this case, we don't track how the photon wave function looks like. In this case, we look at the expectation.
So the photons, so the light is semi-classical here?
Yeah,
Just a classical.
because this one will follow this wave equation.
Okay, so we're mainly interested here on how the light renormalizes the electrons. I see.
And if you want to know, let's say, for example, how many number of photons,
I am sack actually.
basically we can recover the number of photons.
So. Do extra work? No, not devoted.
He will require some trick here.
What are we averaging over there? We're going to have a photon state.
So in this case, I mean like, so in DFT, what we are curious about is like, because now you have electron density and
Yeah. Well,
and then, for example, if you want to understand the physical like quantity, let's say energy.
You're running for
energy functional. If you have an electron density, you can calculate it.
the what?
Similarly, if you want to understand, say, some physical square depends on
observable associated with the photon.
Depends on this.
Right. We're saying that we have a functional of rho and A. Oh, n as a functional of rho dot A. Oh, the name P dot A. We haven't yet derived the functional for A.
Yeah.
Vector potential. That comes later. Okay.
Yeah. So I mean, like here we can.
And J perpendicular, we get that from our QEDFT. Well, no, we already have an expression.
This one is from, for example, this is a matter. So for the matter system, once you have a wave function, you can compute this. So
Sure.
The concept is like this. So I have a we also have a photon system, which is also non-interacting one. And this there's a mean field. This mean field comes from
Yeah.
And you
Cone
have-
sham, Pauli cone sham.
yes, and then you have also external potential and artery exchange correlation, and also photon exchange correlation.
Yeah.
Yeah. So this one is like a mean field scalar potential, and you have a vector potential on this vector system. But at the same time, still okay. This is inside.
Oh, no, that's the guy.
You do time dependent calculation. Something like J external current. There's an external like this. So this is complicated photon system. Also has and then you have the
And hence you have the self-consistent feedback.
yes,
Okay.
and then you have to have exchange correlation current to get this out.
It's good to know.
Yeah. One day I'll come next in the
Yeah.
school. I see. Ah, thank you.
Sample tastes from around the world.
You could go to normal. You go where? All these neighborhoods I've never heard. Chinatown, never been. Change this. So it's like the generic. Oh, start. Deep cuts. Oh, I
But I'm
yeah.
not like,
I mean,
none of the decisions that you made. Large amounts of time. I see the strength, I just see the practice. I will show up. and do what needs to be done, but I mean, it's exciting to travel. Because James is James. It's not like. I don't understand. And then.
它的公司优化才但是不在底，但是你看它回到之前，
rhythm or she's just.
本身就说它本身就是
He has a lot of opinions, which are like usually all over the place. You need to like take the time average of those opinions, but the problem is like when those opinions correspond to things that need to be done in like the immediate, like the immediate near term, then it's good. luckily for the.
Not usually a reaction I expect to see.
Absolutely necessary for me to. Everyone around you. It's like I better not get anything wrong. Something in between. Like, it's like that's hardcore. No. It's been like a couple hours and I haven't done that yet. I did like the duo.
So those who are still working on the notebook, now I put the answers to reduce the frustration. Sorry.
Twice. She just kicks it.
So check. I like doing super fast games. Or making a move and then doing one move and your queen immediately is gone.
Was the move at least useful?
Jump. 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 You tell me. This is the environment. Do you work it? It's infiltrated, unfortunately. I don't. I was.
Oh, never mind.
What? He was at USC. For some reason, he moved to New Mexico. Don't touch mine.
And if I like have samples, so then this
No, he asked for my supplies, so he asked for my proposal. Stuff. I still don't understand.
appreciate that. I was like,
It's invasion of privacy. We still have some rights in this country. Some, not a lot. Same as yours. Same situation. That's true. And then you're gonna become a state. What?
Stealing your pineapple. Look at it, sir.
Purple pineapple.
Pineapple.
Ah,
Can you read?
it's my generation.
Because in the code, the exchange for a function of.
No, I don't.
If you're not trained, you get trained to have no reason.
Yeah, because in this case we are looking into the ground state, and we can always choose.
Oh, no, like that. You can't. Like other people can't.
That's currently the A.
Like there's a bunch
is
of
a
experiments.
constant. So in the function system, you have a vector potential which is constant. You can always choose like a gauge on the wave function to get rid of the A vector potential. So that's why I mean like that's why
Not like using a second.
no. Yeah, I mean like in principle, you if you want to use this form, basically the problem there is like we don't know what is the circulation current. Yeah, and that's quite.
No, like there's no like the self-consistent way for
Yeah, and in order to get this one, then you have to figure out what kind of like approximation.
Is that what we're doing?
Yeah, and if you use this one, then it basically becomes so you will basically you will becomes a density function.
the original exchange for a function.
I think it's because in this case, because we are looking into the ground state, and the ground state A there is a constant, so that's why we can choose a gauge to get rid of the A.
So basically that means J equals 0.
Because there is no external, like the total system, there is no current.
Black phosphorus, so
There's no E.
There's no no. No current, so no current, so no mechanical.
Yeah, I mean like because it's a ground state, so if you have a material inside gravity, there should be no. Yeah. Yeah, that's right.
So didn't fully understand the result. So if I look at this result, so it seems like I have a
Because the reason is that
why is always
Oh, really?
never heard people saying stuff.
so there's two two things you can consider. Like one is that there's a phenomenon called charge localization. So charge localization means external magnetic field, and you isolate somewhere, and basically the electron will try to accumulate around the. Okay, so this is a so-called charge localization, and you can use they kind of like a phenomenon to understand this. So that's why the charge becomes localized. So effectively, it seems like the potential becomes deeper. So this is the first. One is like
I developed a little bit when I was at David's group party. That's when I did that.
So what I'm trying to do.
David Sherrill. Oh.
So if you look at like the fluctuation, we roll like this. We're going to see something like, for example, if I have
For doing DFT deserves a medal.
Yeah. That's a good idea.
Yeah, absolutely.
yeah, something like this, and effectively it seems like it's something like that. And if you expand this one, you are going to see it's a plus, and there should be a minus.
It's
Something like
yeah, it's
immediately you are going to see this one is very similar to.
Well, that's good.
And kinetic energy is a positive one, but here you have a negative one. So it means if you have a quantum fluctuation, it looks like it's trying to reduce the kinetic energy.
I made my project so
Because yeah. Yeah, you try to like reduce the kinetic. Yeah, and if you think about the kinetic energy is reduced, it means that the physical mass of the electron, yeah, it increase. Yes, yeah, the physical mass of the electron increase. So that's why I mean, okay, so this is linked to another picture. So it's like if you have an electron enter into
It's like shows.
yeah, yeah. So if you have a cavity and if the electron go through this fluctuation region, if you like if you use a particle picture, basically it start to pick up those photons, and it will become some more heavy.
my first project.
I guess.
Yeah, because initially, if you haven't put inside the cavity, basically you sum the total both energy. Basically, it's like this value, but now you turn on the interaction.
I'll do it all. Find that even lower.
Yeah, we should have known.
So that's why I was using that the quantity state of
And yeah, because you need to turn on the interaction. I mean, like, if this is true, that means you have, let's say, cavity, you have a material, and if you will become intense, and then basically means if you put like this, and you will push up. I'm not so sure whether people can actually measure the force. Because if we put a material inside a cavity and the energy actually becomes lower, it means there's a force.
And then it has the dimensions of my number of crystals.
calculating real
Yeah. Yeah, without a yes. Yeah. still feel like somehow we should recover A, otherwise there's some because it seems like for a different position, and once you move your position, it means we have to use another gauge. So there's some.
Oh yeah, you don't have the 10th notebook yet.
I mean, like we haven't. Because you already see work as the correlation current, and
Instead of working on the
for,
numbers, you can
it will
go
becomes a current density functional theory. And if you look into something like an open source code, probably you cannot find any like current density functional.
my best understanding, but it's unclear.
Which is great, like, this person is doing like research on functional, just in a very general.
I think
How you should go about deciding. Also should make the case for like potential density function.
Is there a way to end the Jupyter jobs from the browser, or do you just have to go into our account and
You
do?
go to file and then hub.
Ah,
Last week.
what? Sorry.
Didn't kill your job, like, speakers have ever like witnessed.
I was just joking, Kyle. Don't take this.
Okay.
But when I was writing this, Antonio, my office mate,
Yeah.
asked me the
okay,
same
so
question.
now we are going to
Oh, really?
go to the tutorial section, and the tutorial section basically just follow the. I already put like the tutorial in the GitLab. Okay? Yeah, Git repository. So if you go to like a Octopus tutorial, then probably you are going to see there's a directory called cavity model by band structure. And remember that you have to turn on 4 cores. Okay, when you use a flare iron Jupyter Lab. Okay. Okay. Let me turn it on. Okay, so if you are lazy, then you just you just run everything, and then you are going to get a band structure at the end. And if you don't care about this, then you are done with the tutorial. But if you are interested in what's happening in like details, then you can read through the tutorial, like the Jupyter notebook. Okay. Okay.
Once, like I tried going through tutorials, that was like a few years ago. Actually, maybe 3 or 4 years ago.
Yeah, I did this tutorial, but I don't use it on my daily life.
Oh, and that's good. I prefer it.
Oh, so this is the first part, no? Very disciplined. Okay, okay. And direction.
Or the cavity.
It defines the way the cavity couples to the matter. And then you said how you
No.
separating cavity and photon.
With, and like the size of the cavity does not really matter. It's just.
No. In the end, all of those things are incorporated into those three, or however many parameters: polarization, frequency, and couplings. That's polarization. Couplings, yeah.
Do you select four cores? Four cores.
Oh, yeah, yeah, four core, yeah. I don't know. Right? Because I before
I don't know, make it. Yeah, let's go out again and try. No, hub control cell. Oh, wait, that needs a better solution. Can you go?
Yeah, Diane has like handles this entire schedule. Really? Yes. So if you talk to
Stop the
Diane,
server again.
So if you don't have any question and already finish everything, so feel free to leave to enjoy the evening. Yeah, and then but I mean like I will stay here until 5. And if you have any question, just I will go.
Yeah.
log in there and say,
And then see. It might take, the instructions, was it a different?
Yeah.
So I think it was written that for the octopus tutorials, you had to read.
It's okay. I think, yeah, you will see,
Or it would be
I think it's just some, like a symmetry operation in octopus, they use this. I also got this, sure, make a new cool. Thanks.
Yeah.
Yeah.
And now I'm trying to do this. I hope it works, but just thinking like.
What is the physical?
Well, I was actually thinking the numerics. Thank you. Hoping like, why is this bad structure? So what is happening here? What happened? Not a lot, right? So that's one of the main things that triggers changes to the ground state, or they go mostly with length of square. So unless the company is,
This one, what is inside? Do you know?
so you can try to rerun this again with a higher company, or this point, the ability and the point of conduction. I actually don't remember.
Electron photon interaction. So we also want to add additional things like this. And but because in this case we don't have,
The main thing is to think that
so we don't have to worry
you
about
have these effects on the blend structure as well. They're minor because the content is shrinking. Even though in that case it is already
in order
quite
to
small.
compute this
Might
one.
be factor.
These calculations are one is without cavity
Yeah.
with cavity. Why does it say?
So, and then how do you get it?
Surprise, whatever you want.
Yeah, so I mean like the
I guess it's just.
Yeah, the run
from this guy.
is
If you have a more electrons, you have to sample
and the other ones
the
outside.
electrons.
Uncovered.
So you are going to see there's a
Always calculation.
until you do
Yeah,
like
it's just this, the
conversion
regular thing that you
electrons
run.
to, some threshold, and the threshold basically defines by itself.
Yeah.
So usually it's like the density difference is probably like
Basically, it's very, very minor, but I think the point is,
smaller than 10 to the minus 6, like usually things is already
in
conversion.
certain
You can
cases, this is
also
enough.
set it like a more strict
The energy.
I was just thinking of changing, like, I think back a few you gave a reminder that when you try to get it to converge, some certain superconductors as you incorporate some tricks.
Oh, yeah,
Just curious.
Oh,
What kind of tricks would
so
define
you
these
can see like this one. This is a
So, okay.
But that does not seem to be the case with.
So that's what we're gonna see too. If you go back to notebook 7, at the end of notebook 7, there's an exercise there that does exactly that. So what we're doing here is instead of using, like, we assume that people
there are
already use
many
the microscopic
tricks you can solve this
and the mode structure. In this case, it's one mode with that frequency and that coupling strength.
there's a
And then we can run that. So basically what we're doing is there's this two step.
it depends on this.
Mirrors. Stuff. The first step, you forget about putting anything in between, and you get what the electromagnetic environment is.
I mean, like this is as you say,
So
it's
you
a
use
equation
your
problem. So because mathematically, this one is
we just assume something.
if you have any techniques to solve this problem, that's you can try.
Final trailer.
What he actually talks about is sometimes you are going to see there are sometimes for the system the energy for example the system can go to say you have energy which is very close, so the system can
At the end of it,
reach this local minimum, and sometimes it can reach this local
It's just you just hold the cells.
generate
through the optimization process.
the mode structure or all of the nodes
local minimum.
for a realistic
So we only can see
structure tomorrow.
Like Ron?
For the PDF, for the linear response.
to find the global minimum.
But you're right, like it's just done. Push all of those things under.
So
Is Rhino actually green in my screen?
Want to understand why is this one? What? Localize.
loud screen. Imagine there was a cassowary just hidden somewhere, and like this just shows how terrible being.
So they are
Well, it's basically running.
so what is they say if you have a laser, there's a phenomenon called charge localization. It means if you have a laser which has oscillator along this direction, basically the electron will try to localize around the
Restart.
There we go. Yeah.
Yeah,
it's
it's
like in
just
this case we
warning.
have
No, could you
fluctuation.
warn?
I was gonna say no, they like count like some 4 or something.
But I mean, then my next question would be why does it last?
So it seems that you mean like if you have
What
a
Trump says
laser,
in soft particles.
like a there's a high chance it's good.
That's especially around now. It's like it's not too hot. It's not cold. It's a little
This is like
all weather. I don't think the foliage started to change yet.
enter into this
It gets really nice.
It's just like fluctuation. So electron will pick up the photon cloud.
A little bit, but eventually.
This direction, like if linear polarization is along this direction, that's really that's more like electron and the photon like exchange each other. So electron will becomes massier. Like
I think he's trying to finish his
direction. So it means the electron electron physical mass becomes
defend this winter.
and you will try to find the local crash. That's why the electron wave function becomes more sharper.
You said it's good, your screen.
The way
You just want to take a whole walk.
because the fluctuation basically, if you look into the mathematical formula, you are going to see the fluctuation is a quantum X.
Oh wait, really? Yeah.
So
So Brian Cranston. Huh? So Brian
once
Cranston.
you can any energy reduce,
Who's that?
the physical mass actually
Which
so
one?
it's kind of like
Walter what?
They're not hunting.
Definitely.
Did you? I didn't turn on. No, he was trying to like hide his face because like a lot of people were looking at
around your house.
didn't want to bother.
Yeah, he's trying to lie to get through this.
You are. Raise your hand.
I've also seen one of the things that would make it even more
That's why it's.
Yeah,
it's literally.
So.
Yeah, the guy would.
Oh, I see.
Can you go to like there's a
I would have asked for like, yeah, but he was like trying very hard. He was walking with someone. Hide his face. That's where he's trying to hide his face. That's like.
Why couldn't it actually just film the
That's kind of what I'm doing right now.
in this case, we can only solve for one electron.
Oh, yeah, yeah.
If you have a more electrons, there's no analytical
Right.
solution.
Well, he always jumps. What do I do? No, I come in.
Use one electron in the
Where
example, you can also do this. But the problem there is like we are going to see you divided by the density.
Come on. I thought it was normal. I thought he does that every single day.
Actually,
I had to write about it for my
Duh.
Can't be so. For using it. We're gonna go.
You say a school of fish.
Yeah, yeah, you say a school.
Really?
Yeah. We're gonna go and.
Yeah, finally.
yeah, there's a
Yeah.
Kevin.
What is it?
we are going to see what divided by the density. And like in one.
The first is the convergence.
You look into the density, there's a summation which is very close to zero.
Yeah.
And only divided by zero, you will become very large, and you will become numerical unstable.
I think.
Yeah, and then there should in our group there are someone yes, some trees so that's why we make it easy. You can try. You can try. And you are going to see you are asking.
But I guess it could be interesting to consider. Try to guess what the solution if I use the
Yeah.
just from
Like,
I thought it was gonna be fine. Just really adjust it in the end. Seems very hard.
so instead of it being like,
Like where are you from? Oh yeah, but like what the I don't know how big it is compared to super small. Anything out here. I mean, that's why I was curious, like even what said, but immersing the relative. Yeah. There's not much to do there. Right? There's a lot of people there. But I bet you can beat the view or like it's surrounded by mountains. I would assume.
benchmark.
I didn't find where the outcomes.
I think it's inside state. There's info.
Seeing the hills were going. Sure, you can take the train. It's not ever.
First can't get
Oh, should have voted.
I use calciums.
Oh, I see.
Calciums are fast. And it's
Yeah, so they are almost done with the tutorial, so they are going.
Okay.
Yeah.
why do you want crystals? Just use individual molecules.
Okay, okay.
Because all the speakers.
Okay, okay.
Yeah, but then we're getting crystal. Just
No.
together and call it a crystal. It is solar periodic. Very soothing. We can wait as well.
yeah, so you like
Just use a big unit system.
that like breaking one. Like those.
You're getting in here? Trees.
Well, I did
Yeah,
use
actually, we definitely have super, but yeah, something like.
They don't tell me right away.
Oh, but after 2 hours.
They said they're taking a break. Said or they're taking a break. I was expecting that already. So.
Yeah, the issue here is like because if you run outside the caves, there's a
Yeah.
I've heard stories about people.
so what I want to say is like because if you look into the energy,
Yeah, that's.
energy difference is like when you go to the
How often, actually?
This hotspot generates.
I haven't had a show.
you see I already subtracted
Zero. Yeah, that's.
How do you?
I mean, that's a lot of. But you said the electron usually where it's zero, that's also interesting to have any exchange.
It's based on.
He's free tonight, but he's sick.
And this he just sacrificed.
Just run that.
which ones
This fire is from, I think every no time that somebody else outside of the inside of nowhere else.
The last tricks, yeah.
Every time that
Because honestly, I think that means if I put into the country,
Yeah,
I will gain.
Or is it like
Yeah, some numerical tricks people
Because
usually
you
don't write
cannot
so
write.
much about it.
Yeah.
Just boring, but it's important.
Yeah.
So you have to go to the appendices or the supplementary information.
I still have like research
I mean, like the energy,
Danish guy in the Hamburg who did a lot of that. Invested like years.
Currently,
It was mostly
what we
about
do
periodic
energy. So
So
we feel like the energy
I don't have any
is not-
exams.
because the problem is like if you do, let's say,
I mean, you can go to
actually
the,
help.
and
You have
when
to
you go back to the.
I do have health insurance, yeah. It's not good
you
health
start
insurance.
from this energy.
what also
Functional
helps
derivative, then you cannot go back.
Yes. That's like United.
not only
It's
find
like the
the
standard.
theory,
Yeah.
by derivative usually close to zero
Because
as well.
what we do is
Yeah.
like we use